Hey everybody, welcome back. Today I'd like to talk to you about two-sample hypothesis tests. This is when we've got two different groups of data and we want to compare things between them. Today we're going to compare the averages between two different sets of data. That's a little bit different from what we've done in the past. In the past, we looked at one set of data and we were testing hypotheses about whether the average was equal to a particular number or bigger or less than a particular number. Now, that's all well and good, but in most real-life statistics, what you want to do is compare two different sets of data to see whether they're different. For example, you might want to compare the results from a placebo with the results from a particular drug that you're developing. Or you might want to compare the effectiveness of a marketing campaign versus not having a campaign, or maybe two different marketing campaigns. Comparison is kind of like the bread and butter of statistics, and now we're finally getting into that in this slide deck about comparing averages from two different data sets or two different samples. We do have to consider a couple of different scenarios. First, we need to know whether our samples are independent of each other. Like, did you just draw one sample and then a different sample with a different group of people? More than likely, that's a possibility. And then you need to wonder, well, these two different groups, do they have the same standard deviation or the same variance and we're just comparing the averages? Or can those two things differ not just in their averages, but also in their variances or standard deviations? We got to take that into account. Finally, if the samples aren't independent of each other, they might be what's called a matched pair. And that, for example, comes up when you're doing a pre-test and a post-test. For example, in your class, your professor might start out at the very beginning of the semester giving you a little quiz just to see where the class is at. You know, how much of economics do you know, or how much of history or statistics or whatever, and then ask the same group of students the same questions at the end of the semester to see if any learning took place. Well, that's different from the independent samples, because in that first independent samples case, you had a completely different group of students, one that had the treatment and one that had the placebo, whereas in matched pairs, it's the same students doing pre and post or something like that. The formulas are a little bit different. The devil can be in the details. I will say that the overall picture is still the same. Right? You still need to tell me what the hypothesis is. You need to state at the outset what the significance level is. From that, you want to calculate critical values. Critical values are going to be calculated a little bit differently depending on all of these different scenarios that we're looking at. So that part will be a little different, but the concept is still the same. You're still going to need to collect a sample, in fact, two samples, and now we're going to have to calculate two averages or two means and two standard deviations, each using two different sample sizes. So the test statistic will also be calculated a little bit differently, but the fact remains that you still need to calculate a test statistic. Now, once you've got your critical values and your test statistic, everything, there's no difference. You need to split your distribution into acceptance and rejection regions and see which of those two regions your test statistic is in. So big picture, it's all the same. Details can be a little different. Your test statistic is going to be different and your critical values are going to be different. So we can just look at very simple hypotheses that might ask, is the average from one group of data the same as the average from another group of data? And if our null hypothesis that, there is no difference, the drug does not work, it's no better than a placebo, then the averages should be the same. Now we can express this equality like this right here, where if we just subtract mu2 from both sides, right, subtract mu2 from both sides, this becomes 0. And so we have mu1 minus mu2. mu1 minus mu2 is equal to 0. So this is actually the conventional way of expressing the more straightforward mu2 is equal to mu1 kind of idea. Now, one reason why we do it like this is because then our null hypothesis is kind of similar to before, where we had that mu is equal to a particular number. You know, it could be A, could be B, could be 0. So we've got some statistical quantity, some parameter that's equal to 0. And here we've got the same idea. We've got some kind of statistical quantity, and it's equal to some number, maybe 0. So we like to translate from, you know, more common sense mu1 equals mu2 to more statistical practice, this difference here. Okay, so that's one difference in how we set up our null hypothesis, and it's a minor one. Our test statistics, now those are going to change, and on the face of it, it's going to look like a big change. It's not. Our test statistics before, when we had one sample, we had our sample statistic, we subtracted off the hypothesized mean, and then divided by the standard error. Now this general kind of formula carries over right here. Now what we're looking at is the difference between two sample averages. So you can define the average difference to be x1 bar minus x2. In other words, the average from sample 1 minus the sample from average 2. The average from sample 2. Then take the difference, and that's your average difference. Subtract off what you hypothesize the difference will be. That's this guy here. And then divide by the standard error. The standard error will be, that one will definitely look different. Right? But the idea is equivalent between the one sample approach and the two sample approach. We've got some sample statistic, we subtract off the hypothesized value, divide by the standard error. Sample statistic, divide by the hypothesized value, divide by the standard error. Now, how are they different? Well, before, the hypothesized value was really just the average from your sample. Now it's the average difference between the two samples. The hypothesized value used to be a particular number. It's still a particular number. It's now just that number represents what kind of difference you would expect from the two samples. The standard error is going to be, that one's going to be a little different. Now that standard error is going to be different on a whole bunch of different kind of scenarios, the ones that we mentioned a couple slides ago. So let's just say that we know what the standard deviations of our samples are. Sample 1 and sample 2. And let's say that they're not equal to each other. These are two different things. Then we've got to tweak our old formula. The old formula for standard error, when we had a single mean, was the standard deviation of the original population divided by the square root of n. Now, I just want to express that in a slightly different way. Just remember that the standard deviation is equal to the square root of the variance. The square root of the variance. And so that's all I'm writing here. I'm just re-expressing this numerator as the square root of the variance. I do that because then I think it's a little bit more obvious where our new standard error formula comes from. It's still the square root of variances divided by the sample size, except now we're kind of just taking kind of like an average. We've got the variance of x divided by its sample size of x1, the data from our first sample. And then we're adding to that the variance from the second sample, again divided by the square root of n. Right? We're just going to be taking the square root of the sum. Be careful not to do this. You're not going to be doing square root of one plus the square root of the other. You can't split up a square root sign like that. Maybe we don't know what those parent standard deviations are. We believe they're not equal to each other between the two groups, and we have to estimate them using data. Well, that's not a big deal. You've got your data set. You've got, let's say, the drug. Let's call that x1, and the placebo. That's x2. And you've got data. I don't know, 5, 10, 11, 12, 9, 8. And then for placebo, some other data. You've got, let's say, N1 of these, N2 of these, different size samples for the receive the drug, and different number of people who receive the placebo, and that's fine. Our standard error formula is very familiar. It was just what was on the previous slide. The only difference was we used to actually use the known standard deviation. But now we don't know these. We have to estimate them from our particular sample data. So we're going to just replace sigmas with s's, and you continue like before. Almost like before. The degrees of freedom are going to be different. Degrees of freedom now, you estimated the average from the first sample, the drug group, the average from the second group, the placebo. You also had to estimate the variance or standard deviation from the first group, the variance from the second group. You had to estimate a bunch of these things, and now you've got two different sample sizes. You've got the sample size from the drug group and the sample size from the placebo group. And so, it's not just a simple matter of number of observations minus the number of estimated parameters. You got a bunch of estimated parameters, and you don't know what your sample size is. I will say this. The formula for degrees of freedom is complicated. It's kind of ridiculous. And, this is why we like statistical software, is it can do tedious calculations for us. So I'm not even going to show you the formula for degrees of freedom in this case, because it's nuts. Moving on. Special case here is we don't know what the population standard deviations are, but that we believe that whatever it is, they're going to be equal. All right, then our test statistic, our test statistic still follows this form, where we've got the average difference minus the hypothesized difference. And then we divide by the standard error. Now this is our observed difference. That's the average difference from our data, minus what we believe to be the hypothesized difference from the averages of those two groups. That's this guy here. The standard error thing, that guy's starting to look really, really complicated. Before, the standard error was this, S1 squared over n, S2 squared over n. Now it's this monstrosity in the denominator. There's some parts that are kind of similar. We're still got this, divide by n1 and n2. Left those out. Kind of have that thing going on. To try to make sense of this for you, I just want you to focus on the part that's inside this parentheses. And in fact, let's simplify this a little bit. Let's just ignore the fact that you're subtracting by 1. Then what you have is S1 squared times N1, N1 minus 1. Extend this, plus S2 squared N2, N2 minus 1. All right, so we're just going to ignore these negative ones here just for the time being. So what do we have here? Let's split this up. So we have S1 squared N1 over, and oops, I said I was going to not subtract by 1. So we have N1 plus N2 plus S2 squared N2 over N1 plus N2. Now that definitely looks simpler, but then again, probably just because we forgot that -1 bit. But I want you to just think about what this formula means here. Let's say that we had 20 observations in group 1 and 80 observations in group 2. Then what's N1 plus N2? That's 100. Okay, so we got 100 observations total. N1 divided by N1 plus N2 plus N2. Well, that's 20 over 100. That's 20%. And N2 over that sum is 80%. So what this thing really is a weighted average of the variance from the first group and the average and the variance of the second group. All right, so 20% from the first group, 80% from the second group. And those weights are basically given by the relative frequency of the two groups. That's what's going on here, except each sample size loses an observation. That part isn't important. It's important, but it's not critical to understanding what's going on. So this here is kind of like a weighted average of the two standard deviations. Right. And then we're dividing by essentially something like the sample size. So that's a standard error still. That denominator, this whole denominator here, that is your standard error. Now that one's starting a little complicated. Thank goodness the degrees of freedom is now cake. Right? Previous slide, I didn't even show you the degrees of freedom. So this time I can show you. It's the total sample size minus 2 rather than minus 1. You're subtracting 1 from the first group, 1 from the second group for a total deduction of 2. All right, so we would have 100 observations, 20 from group 1, 80 from group 2, minus 2. So you would have degrees of freedom of 98 in this example. But man, that standard error thing is just ugly. Like, how are you supposed to memorize that? You don't. You don't memorize this. Nobody memorizes this stuff. I mean, even if you're going to end up doing this by hand, which you won't ever do, you'll flip open a stats book and you'll look up the formula. And no one's going to be doing this by hand either. At some point, you get to a bunch of questions where it's just not worth it doing it by hand. You're going to just start doing it on a computer using statistical software. So something like Excel is starting to look pretty good now. And so, in fact, we're going to be using Excel a lot. I'll take you about halfway through an example by hand, and then we'll switch over to Excel for all the details. So here's an example that's kind of on my mind lately. Frankly, because I'm in quarantine, and maybe you are too. And by the way, this is why the hair looks like like a Bob Ross kind of thing, and I'm in the guest room. So COVID's going around, and everyone's wondering, like, is this chloroquine any good? I don't know. We still haven't learned that yet. They're hoping to tell us in a little while. In the meantime, what they're doing is tests. And what I'll walk you through is kind of the nuts and bolts of the kind of statistical test that they're doing. So one of the things they're looking at is, if you were going to give chloroquine to some patients and placebo to some other patients, and let's say that all of the ones that you give it to have been intubated. Well, you know, let's just say for the sake of the simplification here that they all get better, which isn't the case, but just keep the example simple. They all get better. But what we're really hoping is that the chloroquine speeds up how quickly people get better. All right. So some group of people gets the placebo, and they have an average, number of days till better. We'll call that mu placebo. And then you've got a different group, let's say with, we'll call this sample size of M. They get the chloroquine, and they have an average number of days. And we'll call that average mu sub chloroquine. Now, the only reason why we would even consider giving someone chloroquine rather than a perfectly benign sugar pill is that we expect chloroquine to kind of speed up the process of getting better. So our research hypothesis is that mu from the chloroquine is less than mu from the placebo. In other words, the number of days that you're, super duper sick and have, you're on a ventilator is less than the number of days if we give you nothing. So chloroquine speeds up your healing process. So that's your research hypothesis, right? Mu chloroquine is less than mu placebo. Let's just subtract off mu placebo from both sides so that we can express this in a little bit more standard way, where we've got some statistic is less than a particular number. So here we've got like a one-sided hypothesis kind of situation. The null is going to be that chloroquine doesn't speed up anything. It's at least as good as a sugar pill. So we get that equality sign. And don't forget, you're actually giving someone chemicals. So it might actually make things worse, right? Where you took someone that was really sick and then you dosed them with, an anti-malaria drug when they weren't sick with malaria, and so it did crazy things to their body, right? Like, we want to make sure that we're not causing harm, all right? So that'll be our null hypothesis, was that the average treatment time relative to placebo is bigger, potentially, or at least the same as a sugar pill. Then let's just say that we're going to test at the 0.01 significance level. Okay, so that's the setup for the problem. Now what's next? You gotta run the trial. So split up your patient pool into people who randomly get chloroquine, people who randomly get the placebo, see what happens. Right? How many days did it take one to get better? How many days did it take another one to get better? So what were those averages? What were also those variances? That's our next step. So let's say that we did that. Okay. So we collected our sample, and then we gave the people the chloroquine, and they got better in a little bit over 7 days versus the placebo, where it took almost 8 days to get better. So hey, this is looking good for chloroquine. 7.16 is definitely less than 7.7. Now, maybe we were short on chloroquine pills, so we could only give enough for 30 people. We could give sugar pills to more people. So we got slightly different sample sizes. We also have different variances. It's not unreasonable to think that if you give people medicine, even if it works, you're introducing this whole new level of uncertainty here. And so the standard deviation from this treatment group, from the drug, it could be bigger than, if you just do nothing. Regardless, there's no reason for us not to think that the variances between these two groups could be different. And so we need to account for that when we're doing our test statistic. We want to use the version that allows for different variances. Okay. Okay. And then here's our alternative. Incidentally, I want to point out that a perfectly acceptable different way to formulate these two things is rather than saying chloroquine minus the placebo, we could have done placebo minus the average from the chloroquine. In which case, number of days for placebo would be bigger than chloroquine. This would be bigger than 0 as our alternative. And then our null would be that it would be less than or equal to 0. These two are mathematically equivalent. Doesn't matter which one you use. Some software has preferences, but you should be able to switch in between these relatively simply. We'll see how that works out in a second. Anyway, let's continue with our by hand kind of exercise. Just repeated the data again. Remind ourselves what the test statistic is. So we're saying we want to take our sample data, this difference between the two treatments in the sample. So we've got 7.16 is the average from the chloroquine minus the average from the placebo, which is 7.77. And now what is the difference according to the null hypothesis? Well, the null was that they're equal. They're the same thing, or possibly even worse. But if they're equal, then the average from one is going to be equal to the average from the other. So if you're subtracting two things that equal each other, this difference here is 0. Regardless of whether you got, let's say, 2 minus 2 or 8 minus 8 or 10 minus 10, that difference is always 0. So we plug in a 0 there. And now we need the sample average from the sample standard deviation from the chloroquine. So that's 4.24. We need it as a variance, so we got to square that. The sample size from the chloroquine, so that's 30. The variance from the placebo, that's the standard deviation squared, divided by that sample size, and then we take the square root of this whole thing. And you just plug that into a calculator, and if I did that right, we get this. Here's our test statistic. Negative 6.98. Now what if I had done placebo minus chloroquine? Well, then I would get a positive 698, because I'd be taking 7.77 minus the 716, so I wouldn't be getting that negative sign anymore. So if you set up your hypothesis with one minus the other, but your statistical software does other minus this, just change the sign from positive to negative or vice versa. It's really straightforward. In our case, we're doing chloroquine minus placebo, negative 0.698 for our test statistic. Okay, now, where were our critical values? In other words, were they here and we reject? Are they here and we reject there? We need to do that. At this point, I think it's actually just a whole lot easier for us to switch over to Excel and start working that out, because one of the strengths of Excel is the critical values, because those depend on the degrees of freedom, and those are really messed up. So let's switch over to Excel right now and keep working. Okay, so I've loaded up some data. Here we've got our 40 people that got the placebo, 30 people who got the chloroquine, and we want to run a test comparing the average from this group with the average from that group. So the way to do this in Excel is to use the data analysis toolkit. I'll have a link somewhere up on top to remind you how to install the data analysis toolkit. For me, it's in my data tab all the way to the right. So I click on that. You can see that it brings up a whole bunch of different options. And at the bottom, these are all of the options that it gives us. So what we're doing then is we have two samples, and these are unequal variances. I don't know how much, like variation adding the chloroquine is adding, like we're adding chemicals after all. So I think unequal variances is the more general case that we should go with. We click on that, and it gives us a bunch of different things that we need to fill in. The first thing is it asks for your two variables, like what your data set is. It doesn't matter which one you choose as variable 1 and which one you choose from variable 2. Now, Excel is always going to do 1 minus 2. And so if you wanted to do 2 minus 1, then just switch the order that you enter these two things in. I think for now, let's just highlight our placebo group, and we'll put our mouse cursor into there, and then highlight the chloroquine group. Now the hypothesized mean difference is 0. Right? That's under the null. There's no difference between these two things. I want to click on labels, because since I included A1, that included this cell, which was clearly not data, that was just a label. And likewise, I included B1 here, and that was also just a label. It wasn't data. So I don't want to confuse Excel. And then we need to tell it where in this entire spreadsheet to report the results. Let's keep everything on the same page. So we'll specify an output range. Click on this particular cell right here, and it'll minimize the screen. Then you can just say, all right, we'll print everything right there. And then bring that screen back and click OK. And wow, it's done a bunch of stuff now. It's calculated some things. Let's get rid of some decimals, just to make this a little bit easier to read. Okay, so it gave us the averages from the chloroquine and the placebo. The sample variances, it reports back the number of observations. Now we haven't talked about p-values yet, so I'm just going to delete these just so that we don't confuse things. And I wanted to do a one-tailed test, because remember, our null hypothesis had an inequality. So did our research hypothesis. We're saying that the chloroquine group has a smaller number than the placebo group, so that's a one-sided test, not a two-tailed test. So let's delete all the stuff that we don't need anymore. Now here's our test statistic, and notice that it's positive 698. Well, that's different from our number. Our number was negative, but it was negative 698. So all that tells me is that what it did is it took the placebo group and it subtracted the chloroquine group. Right? It took 7.7 and subtracted off the 7.1, which is a positive number. And this is going to be just the common practice in Excel, is it's going to take variable 1 minus variable 2. But as long as we remember that, we should be fine. Let's switch back to our slide deck now. So in Excel, it took the first variable minus the second variable, but we entered the first variable as placebo. So we had placebo minus chloroquine was positive 0.698. That's how Excel did it. When we did our formula, we just had chloroquine minus placebo with a negative number. But that's the difference. It's just we just changed the order here. All right, so that's going to be one difference. What about the critical values? That's another thing. Now, if we hadn't used Excel, what would our critical values look like, our rejection and acceptance regions? Well, our research hypothesis was that the average from the chloroquine was less than the average number of days until you get better from the placebo. And so we would only accept the research hypothesis, we would not reject the null, if we got chloroquine minus placebo was massively less than 0. So our critical value should be some negative number in the way that we set up our problem. Now, whether it's negative in here or negative there, I'm not sure yet. Just trying to figure out what side of this thing we want to be. Okay, now let's switch back to Excel for a second. The critical value for Excel is 1.679, a positive number. But you see, that's because we had reversed the order of these two things between us and Excel. So translating that back to our graph, we should have negative 1.679. So, yep, right there, negative 1.679 is our critical value. We would reject the null here. And then we would not reject the null here. Our test statistic is in the acceptance region. Oops. Of the null hypothesis. So what was our null hypothesis? The null was that the average from chloroquine relative to the average of placebo, the number of days possibly greater than, but certainly equal to, a placebo. So this is kind of like the practical stuff that the drug companies are dealing with. They might have this pilot study. They might actually say that, wow, people that took chloroquine are on average have fewer days where they, until they get better. So this seems to speed up getting healthy. And yet, this isn't really like convincing statistical evidence. It's a relatively small trial with 30 people who got the drug, and the variance is pretty high. The standard deviation of 4 relative to an average of 7. There's way too much chance that this particular result just could have happened under the null and just some dumb luck. So, so chloroquine would fail the statistical trials in this situation. So hopefully that's not too real life. Anyway, that's it for now. Thanks for listening, and I'll catch you next time. Bye-bye.